Hi, I'm Talifun. Every AI application has a hidden step that happens before the model or a vector database can do useful work. Before an LLM can answer a question, search a knowledge base, summarize a document, or train on new data, the text has to be converted into tokens. That step is called tokenization. It is usually treated as plumbing. But as AI systems move towards larger context windows, more agents, more frequent data refreshes, that plumbing is becoming a real performance and cost bottleneck. We have made a breakthrough in tokenization performance, a 10x increase in throughput with P99 latency numbers half that of others' best runs. With this improvement, AI and vector workloads can process more text, respond faster, and make better use of existing hardware resources. Tokenization is the step that turns human text into the numbered pieces an AI model understands. If you ask a model a question, the question is tokenized. If you attach documents, those documents are tokenized. If you build a retrieval system, the content being indexed is tokenized. If you use a vector database, documents are usually split into chunks, tokenized, embedded, stored, retrieved, and then often tokenized again when they are added back into the model prompt. And if you train or fine-tune a model, that training data is tokenized before it can be used efficiently. So even though tokenization is not the model itself, it sits directly in the path of the most valuable AI workloads. When tokenization is slow, everything downstream waits. When tokenization is fast, the entire system gets more room to breathe. This matters more now because AI workloads have changed. A few years ago, many AI applications were simple request-response systems that sent a short prompt to a model, then waited for an answer. We have moved to context windows being filled by instructions, retrieved documents, tool outputs, code, logs, records. This quickly bloats the context size. And we do not experience the larger context tax only once. Each step in the conversation must contain the entire context, so we need to provide the previous state and new state context for every call. Prompt caching helps to reduce some of the pressure on the server side by skipping the prefill by using calculated data from KV cache. The server still needs to tokenize, count, hash, and route. In most cases, it's probably quicker to tokenize the full input than look up the cached tokenized input. To maximize throughput, we need to fully utilize inference hardware, as this is the main bottleneck. We can do this by batching multiple separate contexts together and continuously updating them as required. We do this by encoding and packing them together, running them through a batched inference, then unpacking and routing them back. This allows optimizations over padding and scheduling efficiency, which improves token throughput. For larger setups, a single server could manage 1 million tokens, and larger server pools could be in the hundreds of millions. When a step is repeated at that scale, small changes can bring measurable gains. It is no longer just a pre-processing detail before a model call. So the business question is, what does it unlock when tokenization becomes dramatically faster? This is not a small improvement in one hand-picked runtime. The same pattern shows up across the language developers actually use to build AI systems. In Python, our tokenizer is 19 times faster than the next fastest Python tokenizer. That matters because Python is where so much AI work happens. Preparing data, running evaluations, experimenting in notebooks, building pipelines, and running the back-end services behind AI applications. In Node, it is 9.5 times faster than the next fastest Node tokenizer. That matters because Node is commonly used where AI systems meet real users, in API backends, serverless routes, queues, workers, and real-time application paths. And in Rust, it is 9.5 times faster than the next fastest Rust tokenizer. That is the stronger signal, because Rust is chosen for performance-critical systems. A large gain here means real breakthroughs in performance. For a business, this shows up in 3 ways. Firstly, faster user-facing AI products. Secondly, more capacity from the same infrastructure. Thirdly, faster data preparation for training, fine-tuning, retrieval, and evaluation. Together, those gains turn a hidden infrastructure step into visible product, capacity, and data cycle improvements. There is one practical point that matters for adoption. A faster tokenizer only helps if teams can actually use it in the systems they already run. Our tokenizer is designed for the language ecosystems AI teams already use: pip for Python, npm for Node, and cargo for Rust. And in most use cases, it is a drop-in replacement for the tokenizer layer. So the adoption story is not rewrite your stack. It is swap the tokenizer, keep the surrounding architecture, and measure the impact on your workload. As AI systems become more context-heavy, more data-intensive, and more agentic, tokenization becomes a bigger part of the performance equation. Our tokenizer is built to deliver performance while fitting in the tools and languages teams already use. That means lower latency, higher throughput, more efficient infrastructure, and faster data preparation cycles. So if you are building AI systems where this matters, we would love to work with you to improve your workloads. Please get in touch or visit the website for more information.